So let's start. So on Tuesday we left off at which sort? Merge sort, right?
Yes.
So merge sort idea was, what do we do in merge sort?
Split in half.
Split everything in half and then half of the half and so on and so on. We end up with one item, right, which is sorted, right? And then we have a way of just merging them together in a linear time. So yeah, so I didn't mention on Tuesday's lecture that there is plenty of different visualization tools. This is one of them, visualgo.net, but there are other ones, right? There's also YouTube videos of people dancing and sorting. Who has seen those videos? Anyone? The ones they have the dancing, the Hungarian dance? No? Okay, we'll do those during the break. But okay, but yeah, so this is a visualization. You can see this again, how it works in practice, basically, right? So sort, and I want to do it slowly, right? Okay, so the colors means this is sorted, right? So we're gonna split them in different colors, basically, right? Right, and now maybe I'll make it a little bit smaller, yeah, so you can see everything. So we merge these together, and of course we'll merge those together as well, right? So these are so the red means these are sorted. 25, 29 is sorted, right? And of course 35. And here 35 is also sorted. So the question, of course, is why didn't they sort 35, 38? It's of course because we have 10 items, right? So it doesn't divide evenly in twos, right? So depending on your off by one, which ones you merge first, right? It's still log n, but of course it's not going to be perfect log n2 base 2, right? So these of course also need to be sorted. Now let's see if we'll see anything interesting. Right, so the red ones are sorted and the orange ones are sorted. I think here we'll merge these together first. Let's see. Yeah. So linear merging, right? You have to take the pointers, right? The reference to this first element. We know, well, that's the smallest, right? We take whichever is smallest of these. So obviously it's going to be 25, right? And then we're going to take which one? The pointers are here and here, right? So we'll take this one, right? 29, and then in this case, it turns out actually we take all the first three cases are from the left side, but of course it could be from also the right side. So this is kind of like an extreme case when it's basically already sorted. So in this case, the algorithm, didn't have to do much extra work basically, right? So this now the red side is sorted. Well, these green shades are not sorted, right? So we need to do those 46, 43. We of course need to merge them in reverse order, right? So 37 also gets added, right? Now we are left with 546 and it's also nicely sorted. Now, which ones are we going to merge now? Which ones do you think?
The green ones.
Yeah, the green ones. Yeah, the right side. Yeah. And of course, again, the pointers. In this case, it doesn't matter, right? So this algorithm also works for when there is also a tiebreak, meaning there's double case. That's fine too. Some algorithms might have problems with this, but in this case, it works just fine. And of course, the last step, right? Now we're going to have pointers to the 25 and 5, and we'll start looking which one to take first. We'll take, of course, this one here, right? So again, hopefully, the whole idea is you can see this is a linear process, right? You just go through once, right? Slowly advancing to dancing pointers, so you could say, right, on advancing these two arrays or lists one by one until everything is nicely merged. Right. Okay, and now it's sorted. Okay, so now we move on to the next algorithm, the one which is actually was used to be the most popular, still very popular, still very good algorithm. It's called, unsurprisingly, Quicksort. And what's the idea behind Quicksort? It is seems like a little bit harder to implement than say merge sort or than, of course, than the horrible bubble sort, right? But what's the idea behind Quicksort? Maybe anybody knows? Well, I don't want to show you yet, right? It's kind of, in some ways it's similar to merge sort in a way that we are going to be splitting, right? So idea is this: we take some element and we move everything to the left of it, which is less than this element, to the left side, and everything that is larger to the right side. So far so good, right? So what does that imply at this moment? When you've done this element, what's going to be special about this element? It's going to be, it's going to be in the perfect place, right? exactly correct place. Everything else, no guarantees, right? So, of course, we also know we can do this recursively. So if you do this left side and right side, do the same thing. Again, find some middle element. Well, some element. I didn't say middle. It's called pivot element. A pivot element, right? Something we're gonna pivot off. Pivot. I don't know how you should translate this in Latvian. I don't know. Griezties, but no, not really correct, right? It's like our reference point of reference, basically, right? And dot element also will be sorted. And of course, eventually we get to one element. You know, to one element or just one element. And those, of course, already are sorted, right? At that moment, we are done. We don't have to do anything else. That's it. It's sorted. So in practice, this works much better than it's faster than merge sort, but it's same complexity. Turns out it is n log n, still same complexity class, but in practice there's smaller constant factor, right? Less swaps, I believe, right? You can optimize this. It works. It's faster in practice. Maybe you have factor 2, 3, right? You can test it. So let's explore this a little more in detail in our notebook. Maybe I can show you this in here in visualization first this time. Again, so I'll put pause, right? You need pause. Sort on. Okay, yeah. So for each unsorted partition, set first. Okay, and now we come to the crucial point. Which element should we take as a pivot element? And in this particular implementation, idea is this. We'll take the first, right? From our this is completely unsorted. Well, it's unsorted, right? We'll take the first one as pivot, right? So at the end of this first step, 16 will be in the correct place, right? Somewhere here. And in this particular implementation, you'll see how it's done by minimizing the number of swaps. Let's do this. Let's see this. So we'll take 16. So we need to have we'll have a marker. Everything less than 16 goes to the left. Everything more than 16 goes to the right. And the issue is this. We could do this very naively, right? We could say, okay, we're going to move array around, do some movement, right? And that's extremely inefficient because moving arrays like this, right, that costs time and memory and money, basically, right? So in practice, the optimization, good morning, right? Yes. So have you used Quicksort before? Are you familiar? No. Okay, so it's a good time to start learning about this idea. So we don't really, in practical implementations, we don't move the arrays around. Instead, we actually just going to store reference, and later on, it's kind of a cool idea. Eventually, we'll just swap this 16, we'll put it in the right place, basically. Let's watch this in action. So 44 is bigger. Yeah, it's bigger. So 49 bigger, right? So 23 bigger, right? So this purple, right? These marks, basically, these are all bigger, basically, right? 50 bigger, 17. In this case, this actually shows a very interesting moment here, actually, right? 28, all bigger, right? Is this good? Is this good?
It's okay.
It's okay, but it's notice something happens. Everything to the right side. It's completely imbalanced, extremely imbalanced. This is actually the worst case scenario. We chose a really bad pivot, actually, right? This is random, so I'll have to do it again. But yeah, so this is a bad case scenario, actually, right? And this leads us to why Quicksort has, the naive basic Quicksort has a big flaw. If you have a really, really obvious way of picking pivots, right? It could occur that you always pick the first or the last, and your pivoting action is going to be unbalanced. Basically, you end up with a linear operation instead of being log n, because you want to divide them in two halves, roughly. That would be the ideal. The issue is, if you have unsorted numbers, we don't know which one is the middle, right? We don't know. It could be like 28 maybe, I don't know. 28 would be a much better pivot. But okay, let's see this in action. Now, of course, this is basically just like a almost useless operation, basically, right now. So now 16 is in the correct place. That's the only good news. We know 16 is in the correct place. Unfortunately, if we kept doing this, it would be really inefficient. But now, of course, we'll take 44. And now things get more interesting, right? It's not the worst pivot, but it's already a better pivot. So 44, 49 is bigger, okay. 23 is smaller. Notice we did a swap, right? So we're going to be swapping these 29, 50, Do we do anything? No, we do nothing, right? 17, what are we going to do? What do we, we're going to swap probably these two, I think, in this particular option, right? Yep. Okay? Again, we don't care about the order here. So, because again, remember, we don't want to waste time, right? We don't want, at this stage, right? We want to minimize the number of swaps. It's like, we can't, yeah, you're tempted, okay, let's sort it right now, right? You want to sort at this moment, right? No, in the Quicksort, you don't sort at this moment. It's just, actually, remember, just we want to minimize the number of operations, right? So sorting here would be premature optimization, right? I know, right? So 28, what's going to happen? Swap is 50, right? Yep. Okay. On 26, swap is 49. Yeah, you see? On 22, swap is 50 again. 26, swap is 49. Okay, and now the question is, what's the last operation left over?
To swap with 26 with 40.
44 and 26 is going to be swapped. This is an elegant version of this. So again, we minimize the number of movements of the array, basically. We do some swaps, basically. And now, of course, so now, right? So 44 and 16 are perfectly placed. That's the key idea, right? Again, and now we need the next pivot. It's going to be 26 probably, right? Again, because this takes again, the crucial part in Quicksort is how do you pick the pivot. You're going to take 26, right? And same approach for this smaller section. I'll do it quickly. 23 stays, right? Again, we could just imagine it's moving to the left, right? Again, but we don't want to move the arrays, so we just keep using the pointers. 17, smaller, right? 28, right? Stays, right? So 26. What do we do with 26? Probably stays even. It's same, right? And 22 goes to the swaps is 28, right? Probably. Yeah. Okay. So what's the last step now? No, you know.
Swap 26.
Yeah, 26 and 22. And we are guaranteed. We have sorted 3 elements now. 3 elements in the right place. Now, of course, in this case, you see, this is going to be trivial, right? So let's see here. We'll take 22. We'll do one more, 22, right? So again, 23, bigger. 17, smaller. So we need to swap these around. 26, do nothing, right? And now, of course, what do we do? 22 and 17. Swap. So what do we know? 22 is in the correct place, right? 17, well, is in the correct place. Yes, but we don't. The algorithm does not know it yet. It has to look at it, right? If it has a single element is left, right? It's just going to mark it, right? 17 is it's sorted. If you left is one element, hey, it's in the right place. So 23, 26, you take 23 as pivot, right? You check, right? And 23 is going to be in the right place, and 26 is also in the right place. So 28, same thing. 50, and take these 2 remaining, check, and so yeah, like I said, I think the why Quicksort seems a little bit harder is because you are tempted to do some optimization ahead of the time, right? So, but again, it turns out, like I said, because of this, if you choose the pivots in the right, roughly in the middle, and if you think about it, so if it's random numbers, it's going to work great. On average, probabilistically, it's going to be roughly log n operations. However, if you look at the big old cheat sheet, right? You will see the Quicksort's weakness is this worst case scenario is quadratic. And you already saw this. So quadratic could happen if you had it already, well, reverse order, which happens sometimes. Yeah, something gives you numbers in reverse order, it picks the pivot, always picks the worst pivot basically possible, right? So you end up doing this linearly, right? You don't narrow down the search, basically, the search area, basically, where you're going to be pivoting, basically. Okay, so let's look at the implementation, how we could do it ourselves. I think I still have it. Let's connect.
Which is the best sorting algorithm?
Well, Timsort is extremely popular, like I mentioned, right? Which is basically, paradoxically, insertion sort, which is kind of bad, right, itself. It's good, but it's used for small number of items, like up to 50, and then it goes to the merge sort. So it's like it's the best general purpose one, right? But there's a couple other ones, right? We'll see. We'll see. Again, there's no like answer is there's no like one best. It depends of your needs. Are you okay with changing order of elements? And you might at this moment you might not. Is it in order? What does it mean actually in this case? Like you have two 5s or you have two number 26s right here, right? Well, do you care about which 26 is it? I mean, they are basically equal, right? But just imagine if there was some other properties, like maybe my name 26 Valdis, 26 Peter, right? So then you might care, right? You're sorting by this number, by this index, for example, right? But you might care whether the actual elements, they stay in the original order, right? And so there's this property called stability or stable. It's called stable sort if it doesn't change this order. Unstable means it gives you no guarantees. You might end up with different. So 26 might be swapped around, right? So it depends on your use case. Again, also we'll see later on today there are some special cases where maybe possibly we can beat n log n possibly, right? So again, it really depends. If you know something about your data, what you're trying to sort, you can make all kinds of full optimizations. If you don't have nothing, don't know anything, you just know you can compare them, right? Then your stuff probably merge sort is probably like a safe choice. Basically, merge sort will be safe, right? But probably not the fastest if you want to optimize. So yeah, so answer is it depends, as usual, right? So, but Quicksort is again, in most cases, Quicksort beats merge sort. That's the thing. So let's see if come on, am I connected? I am connected. Okay.
But when I use the Python library to sort,
that's Timsort. That's Timsort. And again, that's Tim Peters from Python team, right? Probably second most important Python developer, right? There's actually a big drama about him right now. I don't know. I have not followed the forum drama, but he made this about 25 years ago. And as I understand, Timsort is also used in Android somewhere for some libraries. It's used else. I think Java now uses it because it's very good general purpose, right? So yeah, of course the answer is generally you should use a sort. This is built into your language, right? So Python has Timsort. Yeah, use that, right? Most likely in practice you won't need to write your own sorting algorithm unless you do some deeper research, right? Or unless you have some really weird case where you have a machine which doesn't have a library. Maybe you are doing some low-level work or something, right? There's no sorting, which is, it's possible, right? And maybe you're using general sorting algorithm and you see, okay, maybe you have some special data. Maybe you can do something better, right? Then that's and you need this performance again. The premature optimization is, the root of all evil, right?
Yeah.
So. If you have some special needs, basically, right, then yeah, maybe, you have these numbers, they're only limited range. Then we'll see there's some algorithms which can give you better performance than Quicksort or Timsort, right? So, okay, so let's go to Quicksort implementation, right? So you see the same idea. You have these marks, okay, so this same idea, like we just saw this. So, left mark, right? But it's same idea, but slightly different implementation. Well, you have 54 is our pivot, right? So this says, okay, everything at this moment, 26, right, is less than 54, right? We check 26 is less than, it stays. So this is the left mark and this is the right mark. Now 93, right, moves to the right mark, right? It's larger, right? Right? And you keep going, right? Eventually, these two reference or pointers, right, or index, if you want, in this case, right, you will stop, right? They will meet, right, and then you swap, and of course now you exchange 54 and 31, right? Again, as you can imagine, it's easy if you have to do this from scratch. It's easy to make off by one error again, right? You might do the too much or too little, right? It's easy to do, if you got to do this on, in the middle of night, right? So Quicksort is a little bit harder to implement. So again, of course, you don't really usually have to do it. You just learn about it, right? So this was invented by Timothy Hoare, P-H-O Hoare. Let me see, not Hoare, the Quicksort, right? Yeah, Tony. Not Timothy, but Tony, right? Tony core 59, right? It's still very it's slightly faster than merge sort, right? On larger data, right? It's divide and conquer algorithm, right? And it turns out he developed while he was a student at Moscow State University. Like I said, I still think there is some spying going on because he was from England, right? And he went to Moscow to study, right? So he studied Russian, basically, right? And of course, Moscow State University was a very strong university. But it's again, I'm a little suspicious again. Maybe it's completely innocent. I don't know. But right, I don't know for whom they were accused of working. But he returned back after that he also is not only responsible for Quicksort, right? I think he's still alive also. He's Sir, right? Yeah. He also worked on programming correctness, right? On how to prove that programs are correct, right? He went to, of course, Oxford, and then, like I said, and that's why I'm a little suspicious. Oxford and Moscow, right? There's some stories of, people, going spying. But he worked under Kolmogorov, of course, right? So who is very influential, one of probably the biggest, also greatest mathematicians of 20th century, right? Maybe not quite as Newman, but also very influential. You might have heard of Kolmogorov complexity, right? So Quicksort, Quickselect, core logic is the one which is kind of like structured programming, right? So he's one of the ones who actually pushed for need for structured programming, so you don't have to write everything in assembly or a machine code, right? Yeah, and he big on algorithms, big lots of research, right? So Turing Award in 1980. Okay, right. So going back to Quicksort, right? So hopefully you got this n log n, but worst case it's n squared. So this is a Quicksort, right? We have a list, but again, in this case, I'm going to use the copy because we're going to be testing how Quicksort works. We're going to have a helper. So Quicksort helper is the one. Actually, notice how it works, right? So if first is less, we split point. Maybe you can see this a little bigger, right? So you have a Quicksort actual call. You have three functions, right? We actually call the helper, right? On start, we provide the indexes, right? And then we need to partition it, right? Right, first, last, right? And this is where we do the actual partitioning, right? So not as easy to understand, right? But we already saw this visualization. Roughly, what we did this in visualization. This is what the code does, basically, right? If you have some time. Recommend going through this. Maybe we can run this. Yeah, let's run this anyways. All right, on list, unsorted list. Let's take a look. Is it sorted? It is sorted, right? So Quicksort random. We don't have thousands. Let me run these thousands. I have them here somewhere. Where are my random numbers? I had them in the beginning, right? Where's my random numbers? Oh, here we go. Okay, I have some random numbers. Nice, fresh random numbers. So 2 milliseconds. Pretty good, actually. I believe it's faster, right? Again, than what I did on Tuesday, right? I think it's faster than merge sort. And also, of course, you can do 10,000. Right, 45 milliseconds. And I think we can risk it. Do it on the 100,000, right? So it's not going to be 10 times as slow, right? Because remember there's a little bit of log n also, right? So it's a little bit more than 10 times. So expect, I say 600, no, less, 388. Even better. No. So how about this one? Are we going to risk it?
Yes.
Let's do it. 1 million items, 1 million numbers. I say 4.5 seconds, I don't know. So it'll take about 40 seconds to do this. So 7 runs of 1 loop each. Maybe it's slower. see underneath, you can see how the recursive calls go. You see here the recursive calls underneath, right? Yeah, so 5 seconds, yeah. Okay, so it's not quite 10 times slower, right? It's a little bit more, because why? Because it's not n, it's n log n, right? So you still need also the log n part, right? So if you think about it, it's, you have 10 more items, right? From 100,000 to 1 million. So it should be 10 times more, so 10 times slower. But also you have a log, let's say log base 2 of 10 is roughly about 3 point something. So you expect to be about 13 times slower, roughly, right? So it matches, right? Roughly it is about 10 times slower. And that's very, of course, very rough comparison. Of course, not so we have Heapsort already in this book, but I thought I mentioned this in the new one, in today's lecture. Let's see, this is 3, and we want also 4. I think I mentioned Heapsort also here, right? Sorting continued, right? Let's open this up in here. Oh no, okay, I'll do it here. I'm still signed in here, I think, right? Now, of course, I have Heapsort already, right? So I mentioned yesterday selection sort, right? What was the selection sort? Let's refresh this. Let's see how it works. You have selection sort, right? Right, slowly, right? We are going to find probably either minimum or maximum. I think this is going to be minimum. Let's see. Right. Right. In this case, this is going to be min sort, right? So min 2. So we swap. We put. In this case, we start from the beginning, right? We find the smallest value. Hopefully, you can agree with me that it doesn't matter whether we start. Well, it should not matter whether you look for the smallest or the biggest number, right? You start from one end to another end. Of course, in practice, it could matter depending on how your array is structured, maybe some computer architecture, but theoretically it shouldn't really matter, right? So as far as complexity goes. So again, now we'll find the second smallest, right? One is sorted, right? We'll find the second smallest, right? So orange means it's sorted, right? And we will find 32 is current candidate. So what's going to happen now? 3 is the current candidate, right? No. 9, is that the smallest one? Yes. And of course you'll go to the end and 2. So, right? Now again, 50, 48, 23, right? 9. And again we have to keep going. So here you can see also where the quadratic complexity comes, right? Each time we have to go through and find the current minimum, right? So n squared, right? Technically n squared minus n because we keep decreasing, but it's still n squared, right? Because it's minus n doesn't affect this complexity, right? For large numbers, you still have this dominating square. This 10,000 times 10,000, right? Minus 10,000 is still going to be very close to 10,000. Okay. So idea of Heapsort is, well, we're still going to use this idea of going through finding the minimum or maximum. But what if we could use another structure to pick the minimum or maximum immediately, the current minimum and maximum immediately? It turns out there is such a structure. It's called a heap. Later on in the data structures course, we'll cover this a little bit, right? But the idea is this, it always gives you ability to pick the current minimum or maximum in log n time, right? Not linearly, not like this, not like going through all of them, but going through some sort of tree-like type structure, right? And so we can say, okay, selection sort will use heap, and heap has log n performance. So it's one of those things, one of those tools. You see, okay, here's the tool with complexity log n. Why not use it, right? So in algorithms, like in general programs, you build things from other solutions. So this is one of those instances, right? You use a known structure to build a sort. So the question would be, which came first, heap or selection sort? I believe selection sort came first, and then of course heap. And somebody came up with the idea, of course, you can combine these things, right? Heapsort is actually, you end up with log n. So I can show you the idea. Heap sort here. Yeah, let's do it. All right, but this is going to be not. Is it going to be randomized array?
This you zoom in.
Yeah, let's do the zoom in. Yeah, okay. I'm going to pause it. Yeah. So basically, you do something called heapify. You make a heap, right? You create this tree type of structure. Again, at this stage, don't worry too much about it, right? We'll discuss this more. But idea is that this element is always maximum, right? And there's a certain property of this heap, right? But it's not if you talk about binary trees, we'll talk about those, right? That's actually we're still heaping. Is still heapifying. Step forward, yeah. Or skip forward. Oh no, it's all nicely sorted. No, yeah, it's sorted. Right. Okay. Let's step forward, right? You need to build this tree. Again, I don't want to show you all of these because these three operations, yeah, right. Basically, we're trying to get the maximum value, right? Eventually, we'll have the maximum value. Okay. Right. So 956 was the maximum value, right? And the idea was, of course, that each section, right? This is the maximum value for each section. That's one of the key properties of the heap, right? So it's not sorted, right? That's the thing. It's kind of like it's halfway sorted, basically, right? It's always has the maximum value here, right? And then, yeah, you go back, you go back, you go back. Yeah. So we have two numbers, 956, 952. But again, the whole idea is it's just like selection sort, except you have this cool tree structure underneath. Again, let's not worry about this tree structure too much yet, right? So, so you basically, that's why I'm at this stage. I'm going to cheat a little bit, right? I'm going to use heap q, right? It's built in Python, right? So I heapify, right? And then I return it heap pop. So basically, I just take the top element, right? I take the top element one by one by one by one, right? And this is really easy to analyze. If heap has a property, it takes log n to get the top element and rearrange it, right? So you just pick the top element on whether it's minimum heap or maximum heap, right? You have a sorted sequence once you pick everything out, right? It's almost trivial, right? So it's like you leave the hard part to somebody else, basically, right? Okay, you go build a heap, right? You go build this tree structure, right? I'll just use it, right? And you have a nice sorting structure, right? So let's take a look again at the pluses and minuses. So just like selection sort has this property, this ugly property, Heapsort has property it's always n log n, because again, you need to always pick the minimum element or maximum element, right? So you have to do this n log n times. You don't know how sorted it is, right? It may be perfectly sorted, right, already, right? So you waste this a little bit. So Timsort, so Heapsort and merge sort, again, you most likely don't want to use them if you suspect your data is almost sorted. You want to use Timsort, right? Right? Yeah, so, and hopefully, yeah, so it's Tim Peters, right? Yeah, so Java uses it, Android uses GNU Octave V8, which is V8 is in JavaScript engine in, even, and also the Rust also apparently also used something similar to this, right? So, basically, he used different Tim Peters, he used some of this Peter Mac, so I guess, paper, right? He read it, some ideas, and hey, this is going to work good in practice. So insertion sort, right? And then you have the merge, right? So again, so in practice, very very cool algorithm, right? Okay, but heap sort basically we say, okay, we have make a heap on, then just take element one by one, pop, right? So you check this heap structure, right? And notice here, this interesting moment, this is, I don't know if it's going to be stable, right? Stability, meaning the other values, properties of these items you're trying to sort, are they going to be swapped around, right? Is 126 which 26 are you going to pick, right? If you have multiple tie breaks, right? Are you going to keep the original property, right? So that might be important to you. Might not be, right? So this is a simple heap sort. This is also what's the difference between these two, right? I mentioned this here, right? This is in place. Why? Because heapify, to say memory, I pass in some list or something, and what's going to happen here when I heapify?
Creates heap.
Yeah, but it's linear time, but it destroys the iterable, basically, right? It basically, you don't keep the original, basically, right? So that's the problem, right? Here, I am doing this slower, right? I make a new out of place again. So this idea of, do you keep the original data, or do you just get the sorted data out, right? If you want to keep the original order somewhere, you use this type of sort, right? You keep the original, right? Here, original is gone. Original is basically going to be destroyed. Again, it might matter to you, it might not matter. So, yeah, let's run anyway. 9:40, so we'll take a break in about 3 minutes. When we get to seeing whether we can do better in these sorts. Okay, come on. Oh, it's connected. Slow. Come on, it's slow. Maybe because I'm going to close this one here. Yeah, maybe faster. Yeah, okay. So, AND-list. Yeah. But actually, oh yeah, so heap sort. Yeah, so this one is not going to destroy the original, right? So I still have I'm checking whether the original is still in order, right? So it's still in the random order, which is, because otherwise there's no point of timing. Again, it's going to kind of destroy the timing. All right, so let's do it. 10,000. So do you think you'll get to million? With Quicksort, we could do million, right? Okay, this is Timsort, sorted. This is like the golden standard, like 2 milliseconds. Okay, so it's 3 times faster than my Heapsort, right? And again, I'm already cheating a little bit because I'm using the built-in heap, right? But the Timsort beats by about 3, right? Okay, let's do 100,000. So we expect, okay, 160. The difference is what? 10 times, right? 60 plus some overhead, right? There's a big variation here. Why? Because it's only 7 runs, so it could be 120 milliseconds, maybe 200 milliseconds. Pretty big deviation. Let's do Timsort. So yeah, 5 times. This is 3 times faster. No, it's only 5 times faster already. Pretty good. All right. So before the break, let's do Heapsort for 1 million. So 2 seconds last time, but this is on a Google server. I think my machine was a little bit faster then. Let's take a look. Maybe. So we expect about 15 seconds to take this. Maybe 20 seconds. Yeah, so a little bit slower, but okay. So going from 100,000, right, to 1 million. Actually. Oh, that's Heapsort. Sorry, that's Heapsort. Yeah, that makes sense. So 1.170 milliseconds, right? Times 10 would be 1.7 seconds. But again, remember, it's not just n; it's n log n, right? We have 10 more items. So about 13 times slower, roughly. Very rough. This is not exact math here, right? Just intuition. right? So here, same thing for sorted, right? 440 milliseconds. I'll say it's about 500 probably. $600. Okay, so about 4 times, yeah, 4.5 times faster still, right? So it seems like it's going to scroll through, right? Right. So again, so Timsort beats Heapsort. Again, if you test it, also I recommend you test it against Quicksort, and of course test it against MergeSort. You say Timsort is using MergeSort underneath, right? But again, it's optimized for these cases where you have runs when you have partially ordered data, right? So that's why Timsort works so well in practice. Let's take a break, right? On C, when we continue, right? Let's continue at 10. Let's go at 10, right?
Okay.
Let's go at 10. Let's see if we can do better.